Well, thank you very much for the introduction. So I'm really glad to be here to introduce about our story. So what we are doing, what I want to talk about today is about the social interaction, language, and the brain. Okay. And I have a pointer, I believe. Yeah, okay, fine. All right, so when we talk about the social interaction or social communication, you can easily imagine how different animals are doing that. Like they smell each other, they use odor, and they touch each other and using perception. And also the other stuff like they use the pheromone, for instance, to interact or attract each other. But what is so different for human is for us, we use language to understand each other for the social communication. And you already know that, how much language means to us, because it has a lot of information. It actually provides a lot of information, and it helps to understand each other. So then in that case, what the language means to us and what exactly it is. Actually, it is a big question, I think. So since it's a big question, there's so many different fields that works on language. For instance, like a linguistic point of view, they think that this is the fundamental behavior that makes it human as human. So it is really important. For in the field of humanities, they actually put the language on the top of the pyramid for all the perceptive, or attention, memory, motor skills, and all of those behavior. So this means that they also take the language as the most complicated behavior to understand. And this is the reason why it is taking so long, and still we haven't solved all the problem to understand what the language is, although we know it is really important. From the neuroscience point of view, we actually know that which part of the brain we are using when we are processing language. Using high technology like fMRI and PET imaging, now we know that these regions are actually involved for the language processing, like a Wernicke's area or Broca's area. So for this we know, okay, there are certain brain regions that we are using to process the language, but still we don't know how we are doing that. And there's one interesting research done is like, what about those people who can speak multiple languages, how they are processing language and which brain region they are using while they're doing it. And then what is interesting is comparing monolingual people, they basically have all of these areas, which we all know for the language processing, but they use those regions in a very different way. So while they're speaking, all of these regions are highly activated, which means that all of these regions are heavily connected. On the other hand, the monolingual people, they do have these regions, but they're only using certain region while they are speaking. So it seems that the neural connectivity is making the differences for these kind of different behavior. So this is also what we know from the neuroscience field, but again, we don't know how they actually get this connectivity while they are developing. Because we all know that acquiring language is not genetic. If you grow up in a different country, you become fluent with those languages spoken in that region, and even this language is not spoken by your parents. So what's happening while they are learning the language is also one of the mysteries that we haven't solved yet. But when we talk about language, of course we need to look at human, because human's the only animal we know that speaks language like this. And what we know about the language development in human is they take stepwise development. Like starting from 2 months, they do a lot of cooling, and 4 months old, there's a lot of bubbling happens, and at 6 months they start to distinguish lots of different sounds like M and Ds. But this period, 4 months old, bubbling seems to be a really important step for human to learn language. So I'll show you the movie that how infant and mother interact. So there's a sound comes up. Oh, wow. So I think you have seen this, right? Or you have done this to your kid. So what is happening here is basically the mother or adult talk to baby, and then the baby tried to reply with mimicking the sound. And this interaction is really important for baby to learn language, because if they don't receive that much input from adult, can I go back? There we go. From a mother, then they have lower number of the vocabulary after they grow up. Okay, so then how are we going to tackle this question down without using human? Of course, the human, there's a lot of ethic problem. We can't do everything like what we want to do. So the first thing is come up to your mind is, what about mice? Can we use rodent, which is the most frequently used animal in the lab? And as you're hearing, they do have different type of squeaking. So it's showing a different strains, and they do have their distinctive call pattern. Also for like the baby mice, they do generate ultrasonic vocalization that we cannot hear, but it is important for a mother to retrieve them. But the problem here is these guys, they don't learn how to make this sound. It is innate, they already have it. So this cannot be the good animal model to answer what we want to do. Then, there you go. We were looking for suitable model animal, and now this animal is becoming, very popular among the neuroscientists especially. And this is a common marmoset, little New World monkey that live in Brazilian region. And I'll show you, or make you to hear that, what kind of vocalization they do, and then they do the vocal exchange, which you're going to hear it in this movie. Okay, so this guy is making sound. Now you can hear someone else is answering to his call. One more, it will come back one more time. I hope you heard the last bit. But basically, they wait for someone to make a call, and then after they finish it, they reply. So this is basically, it's not in the screen, but the animal is in the really far away. So this is a fecal they exchange when they can't see their friend, because it's a high pitch, and then they can actually hear it even they're far away. And there are only a couple of type of calls in this movie, but actually they do have a lot of different call types that you can see here. And also these different type of call seems to have a meaning like this. And what is also interesting about these animals, they can combine different type of call types, and then they can generate another meaning. Okay, so what is also interesting about the common marmoset vocalization is they need to learn from their parents how to make a correct vocalization pattern. So you can see here, this is the neonate, 1 day old neonate marmoset, which is a sonogram for their call. And then you can find that this typical yellow call type, which this is a cry call, is very typical to baby marmoset. So you can also see it at 14 days old marmoset, all these yellow greenish color. However, if you wait for them to grow to 1 month or 2 month old, these yellow call, the cry calls are almost gone. And these call types actually transform to this long call, which is a fecal we just heard in that movie. And that's the kind of adult call type that they really need to communicate each other. And the reason why I'm saying that they need to learn from how to make a call from their parents is because of this. We actually do have a big, marmoset colony, but sometimes there's accident, the parents actually neglect and they don't raise. And then in those cases, we, human, raise them. And then those baby marmoset, which was artificially raised, actually show interesting call type, which is here. So this is 2-month-old marmoset, which the human raised, and you can still see a lots of cry call remain in their call pattern. However, this is actually the sibling of this one, and there are no cry calls, but it already transformed to the fecal adult call type. And I hope you can hear it. So this is the movie from this guy, and then once we put them back into its home cage, the sound is a little bit small. Okay, probably you didn't hear it. I was trying to show you or make you to hear that it is making lots of, cry call once we put them back into the cage. So it's basically, he got back in his cage, so he got highly excited, so he's quite happy. But normally, baby marmoset don't use cry call when they're happy. So they're using it in a very different or wrong way. Okay? So then, it was a simple, experiment, just show the one call type, which is exist or not. But in the reality, they actually do make more complicated call type. So this is also not that long, but if you look at this call pattern, it's more noisy, right? But this is a call pattern when they make it when they are separated from the parents. So when they're separated, they make a lot of call type and try to call the mother or father for them to come and pick it up. In that case, we actually make this, complicated call. Actually, this is after they call the parents, and parents actually came and saw them, but they didn't pick it up. So they're a little bit stressed. In those cases, they make this cry call, thick, and trill. So it's a combination of this. But if you leave them a lot longer, So they are like, left alone, and then you leave them alone for a lot longer, and then they change their call type. So now it is more about the cry and twitter. So this is basically like, oh, parents came, but oh, she didn't, pick me up, and then for a little while, like, you have your kid in the kindergarten, sometimes you're late, right? In those cases, they're probably, really sad, but it's the baby cry in a very different way. So probably this is what is happening. So you can see that, I hope you can see that, they do make a different kind of combination of the call, which again means something. So here, this is really interesting, phenomenon that we can actually work on. And also, marmoset, it's not only because they are vocalizing animal, it is also, very beneficial for us because we can generate the transgenic marmoset or knockout marmoset using CRISPR-Cas9 technology. And then actually we are making lots of like Parkinson's disease and also like a developmental disorder model animal. And one of this developmental disorder actually have the altered vocalization pattern, which I'm going to show you. So one of the mutant line that we actually have right now is Rett syndrome model. So Rett syndrome is known as the disease that it happened mainly in girls because the causing gene MECP2 is actually on the X chromosome. So in the case of the MECP2 mutation happens, there are a lot of behavior defect, like a very interesting motor defect, like they just move their hands like this. But what is interesting for us is basically they lose language ability. Okay, so then we generated MECP2 knockout mutant marmoset, thinking this is could be the Rett syndrome model, which is we are still also working to make sure what is the similarity with human Rett syndrome and then also differences. But one thing we realized that the MECP2 knockout marmoset also have altered language developmental pattern that you can see here. So the left side is the wild type, right side is the mutant, and these are the time course that you can see that this yellow bar is actually the twitter call, and it seems that they have less number of the twitter in this animal. Okay, so there are differences that we have noticed, but to really understand what's happening is since they have a very complicated, let's say, grammar and then different call type and the combination of the call type, just chop out small or short period, it doesn't make sense. We really have to cover the entire their time when they are growing, and also we also need to understand or see that how they are interacting with their parents. So we decided to generate this device that we can monitor and record the entire family for 24 hours. So now you can see here, there's only one monkey inside here, but it's basically keep moving around, and it's going to make fecal somewhere, probably soon. And we are basically monitoring that, there you go, it made a fecal. We are monitoring the entire behavior and when exactly or where exactly they made the call. And then we can extract like which call type it generated, and then we can find out when and where they did it and then what they were doing. And also what we can do is after extracting, we can also extract only one call, like this is the extraction of the fecal, and you can find out where also they generated fecal. Now it's feeding a lot. Okay. So this is kind of the device that we have generated. We're trying to collect lots of data. So this is something we can do by ourselves. But what is really difficult to do is the analysis of all of these huge amount of the data. We need to understand, but it's of course just looking at the sonogram doesn't help much. So now we need a collaboration with the people who can model this pattern. So here, sorry, it's a really busy slide, but this is basically what we are trying to do here is we just get all of those call pattern. We can get interaction with their parents, and also we take all the pattern while the development. And then now we can, using the modeling system, probably can find out what's the rule for the marmoset to learn language, or what's how they usually interact with each other, what kind of input they need when they are developing. So this is the plan here. And also to understand how human vocalization develops. We can't just keep using or working on marmoset. Now we need someone who works in human baby. So here's the plan. We also get a lot of human baby vocalization, and also we have to take a lot of mother-infant interaction. And also what we want to do is well, we can't do that much for human, but again, if we make them to hear a slightly different tone, how much ability they have to mimic that tone. So we can do those kind of things, and altogether with the marmoset data and human data, probably it will give us the platform that we can directly compare marmoset vocalization development and human vocalization development. And as a neuroscientist, we actually want to know what is happening inside of the brain. And once again, we have monkey and human. We can't directly compare because anatomically they're a little bit different. To solve that problem, now we have a person who can actually compare, sorry about the residual Japanese here, but this is the human, Diemen, and then this is the macaque and marmoset. So actually he's developing that we can actually compare these brains and find out same region or equivalent region for each of the brain. And at the same time, if we can get like F-Neur's data for a baby, human baby, then we can apply to these information and can compare where exactly the brain is functioning while they are learning language. So this is basically the plan, but once again, it is not easy to do this everything by ourselves, so that's the reason why we have this team. And after we collect lots of the data set from marmoset and also from the human, there's a modeling system comes in here, so we can actually compare, like it's an integration of human and marmoset data here, so we can get what's the similarity, what's the fundamental rule that actually governing the vocal development. And also we can do the cross-species imaging, so we can compare the brain region that we are using each other directly. So this is a really important part for the integration of different research area. Also, doing this, integrating lots of different research area, what we can do is something like this. This is just an example, but now we have a molecular biologist, and then also we can work on lots of molecular, new advanced molecular technology to find out in marmoset brain, which may be able to translate in human brain. Also with this, we can deal with the language evolution or robotics, and also like predict the operation dynamics of human vocal learning. This is basically our ultimate goal. But with the interaction with all of these teams, that you can finally get this thing done. And we thought that this is something we have to deal with till quite recently, but again, this is like, they have to have the input and they start to learn how to speak in the proper way. But now we have to deal with some other input, which is the AI. So now AI can talk to you. I mean, you can ask something and they can talk back to you. And we know that when we are learning language, if you, watch TV, like a Spanish TV, you can't learn Spanish. But if you have Spanish-speaking nanny, normally kids become very fluent. So it's very different from just you're hearing the language or you have vocal exchange. It makes a big difference. But now, ChatGPT, if it start talking, they can talk back to you. They can have conversation. But we don't know how much these things change our kids' speaking or behavior. So there's other factor now we have to consider about it. This is something that I wanted to add here, which I forgot. But this is, again, this is another integration that we need to consider about. And also this is a reason why we really need to understand how brain functions and how brain develops. Okay? All right. So altogether, these are the people that actually worked on this the project. Well, they're still working on it, and these are the collaborators. So these are all from this project is running by the entire RIKEN project. So these are the people from RIKEN and also funding from RIKEN. So I try to keep it short. Thank you very much for your attention.